the two vectors, we're going to take r, remember, I guess I should redraw this. Here's our mass out here at a position r, where x and y are the two coordinates, vectors r. And so we have, let's say the vector r might be the numbers 1 and 3, as we wrote before. That gives us x and y. The velocity is going to be 4 and 1. And the acceleration is going to be equal to 0 and minus g, which of course is 10 for our problem's calculation. Acceleration in the x, acceleration in the y direction. Now, what are the equations that we want to use with this? The equations that we want to use is that, remember from what we had before, the position x at a later time is equal to the position at an original time plus the original velocity times time plus 1/2 acceleration times time squared. This always applies if we have constant acceleration. And velocity as a function of time is equal to velocity in the x direction plus acceleration times time. And the acceleration is a constant. Now this applies both to the x coordinates and to the y coordinates. So let's first apply this in the x direction and say, what can we determine in the x direction? Well, there we know that the acceleration is 0, the velocity is 4, so the initial velocity is 4, a is 0, so we can say that the velocity in the x direction is going to be given by 4, that's the original value, plus 0 times t, so we can just forget about that. So it's 4 meters per second, continuously, for now and forever. It never changes. The acceleration in the x direction is 0, and it's always 0. What about the position in the x direction? Well, remember this acceleration is going to be 0, so the position in the x direction as a function of time is going to be its original position. Now, what's the original position? We're going to say it's at 0. So we're going to start this object out at 0, plus the initial velocity times time. The initial velocity is going to be 4, so it's going to be 4 times t. And so we can forget about this. So the velocity is equal to 4. The position is going to be equal to 4 times t. And this is going to characterize the entire x motion from now on. It's moving at 4 times t, this is the velocity, and it has an initial velocity of 4. Now, while that is going on, at the same time, we can say, we might want to write that in vector form, so let me go ahead and do that. What is the vector r? The vector r is going to be equal to the x component, which is 4t, and we don't know what y is going to be equal to, and the velocity is going to be equal to 4, and we don't know what the velocity in this direction will be, and the acceleration will be, of course, 0 and minus 10. Okay, well, what about the motion in the y direction? Well, this is the more complicated motion. We've already solved the x direction. We know what's happening in the horizontal direction. But in the vertical direction, we just need to apply these same equations. And what would they be? Well, the acceleration is going to be equal to minus 10. We know that, and that's in the y direction. What about the velocity in the y direction? Well, the velocity in the y direction, just like in the x direction, is going to be equal to velocity originally in the y direction plus acceleration times time. Well, what was our original velocity? Well, the original velocity started out, that's like the original position, started out having the value 1. So this is going to be equal to 1 plus the acceleration times time. Well, the acceleration is minus 10 times t. So this gives us a velocity of 1 minus 10t. And we can go ahead and put that in over here for this component is going to be 1 minus 10 times t. And that's going to give us our velocity in the y direction. The velocity in the y direction is given by this. Well, what about the position in the y direction? Well, y itself as a function of time is going to be given exactly like this equation. What is its original position? I believe I forgot to put this original position in for x. So it's going to be 1 plus 4t. I hope all of you caught that. But back up here, we had an original position of 1 for that. It's going to be plus 4 times t. So I had a position where this thing started out at 1 meter along the x direction. And I forgot to put that in. So it is the original position was a value that wasn't 0 in the x direction. It was the acceleration only that was 0. So then I have 1 plus 4 times t. That would give me my x position. Now the y direction is going to be what? Well, in the y direction, I start out at a height of 3. So this number here is 3. Original position is 3. Plus the velocity in this direction, what is that? 1 times t. That gives me the 1, which is my velocity in this direction, upward direction. So I'm 1 meter per second going up, 4 meters a second going to the right, plus 1/2 acceleration, which is minus 10 times t squared. So can we simplify that? Yes. That'd be 3 plus t plus, minus 5t squared. And so that would be the value that we have here for our y position. It'd be 3 plus t minus 5t squared. And so this gives us, as you can see, both our acceleration at all times in the future, our velocity at all times in the future, and our positions at all times in the future, both in the x and the y direction. So if you give me the time, then I can solve this, and I can compute exactly where this particle is. So this is our answer, this is our result. And we can say from this that we have solved the motion of this particle moving under the influence of gravity. But there are other aspects that are important to this problem. You can say, well, this object was thrown in this direction. How high did it go? When did it get there? How long did it take before it fell back down to the ground, and so forth? Do these equations tell us that? Well, they do, but they can be kind of difficult to apply. Let's see how we would apply them and where we might use this one other equation that we know. What is that one other equation? Remember, we had this, we had this, we had this for constant acceleration, and there was one more equation. What was that equation? That equation was that v squared minus v naught squared, final velocity minus the initial velocity, is twice the acceleration times the distance that I go. And this can be very important because it does not involve the time. And it's very useful, for example, in finding how high something goes or something like that without knowing the exact time. But let's think again, what do we know about the problem? Well, it's often useful when we solve a problem like this to say, let's make a list of the things that we know and the things that are unknown.